14 billion miles from Earth, an instrument built with 1970s technology, just measured something that made physicists go back and check their math. Not because the universe suddenly broke a rule, because a 49-year-old machine, sitting in a region of space no human instrument had ever occupied before, found a number that didn't match what theory said it should be. And the gap between that measurement and the prediction has stayed open for over a decade, forcing some of the most experienced plasma physicists in the world to admit that a fundamental piece of how they thought the boundary of our solar system worked may simply be wrong. This is the real story of what Voyager 1 actually measured out there, why NASA confirmed it changes how scientists think about the edge of our solar system, and why, even now, the full explanation is still being argued over. Let's start with the measurement itself, because it's the foundation everything else in this story rests on. In August of 2012, Voyager 1 crossed the heliopause, the outer boundary of the heliosphere, the vast magnetic bubble generated by our sun that surrounds the entire solar system and separates it from the rest of the galaxy. That crossing made Voyager 1 the first human-made object in history to leave the direct influence of our own star and enter true interstellar space, the region filled with the thin, cold material drifting between star systems. For decades before that moment, physicists had built detailed theoretical models predicting exactly what conditions should look like once a spacecraft actually crossed that boundary, models based entirely on indirect observation, since no instrument had ever been physically present to check. Voyager 1's own plasma instrument, the tool best suited to directly measure that environment, had actually failed decades earlier, back in 1980. So scientists initially had to confirm the historic 2012 crossing indirectly, using secondary readings from other instruments. But other tools aboard the spacecraft, along with data gathered years later once researchers found clever ways to work around the dead plasma instrument, eventually gave scientists a real measured picture of what that region of space actually contains. And that picture didn't match the models. The plasma density in the region, just outside our solar system, the actual physical thickness of charged particles filling that specific stretch of interstellar space, came back significantly higher than pre-crossing calculations had predicted. That gap became even harder to dismiss once Voyager 2 crossed the same boundary 6 years later, in November of 2018, this time with a fully functioning plasma instrument still on board, giving scientists a clean, direct, unambiguous measurement of the crossing, as it happened in real time. Voyager 2's data confirmed exactly the same pattern Voyager 1 had hinted at years earlier. Plasma density outside the heliosphere running measurably higher than theoretical predictions, and this time recorded on a completely different side of the solar system, in a different hemisphere of the heliosphere, at a different point in the sun's roughly 11-year activity cycle. That consistency mattered enormously. A single unusual reading might be dismissed as a fluke, an instrument quirk, or a local, temporary anomaly. Two independent spacecraft crossing the same kind of boundary years apart, in different locations, confirming the same unexpected density, is something else entirely. It's evidence of a real structural feature of how our solar system interacts with the surrounding galaxy, one that existing models simply hadn't accounted for. The leading explanation researchers have converged on involves compression. As the sun's outward-flowing solar wind pushes against the inward pressure of the surrounding interstellar medium, plasma appears to pile up right at that boundary, the same basic way snow banks up in front of a plow blade instead of being pushed cleanly out of the way. That compression effect helps explain why the density measured right at the edge runs higher than simple models, which often treated the boundary as a cleaner, sharper transition had assumed. But confirming that the compression is real, and understanding exactly how strong and how far-reaching it actually is, required the direct, physical measurement only a spacecraft sitting in that exact location could ever provide. No telescope on Earth, no matter how powerful, can measure the density of plasma occupying a specific point in space 20 billion kilometers away. You have to actually be there. Why does that specific number, plasma density at the edge of our solar system, actually matter enough to describe it as something that challenges established physics? Because that density and behavior directly affects how much galactic cosmic radiation, the high-energy particles blasted outward across the galaxy by ancient supernova explosions, some of which detonated millions of years before our sun even existed, actually manages to reach the inner solar system, including Earth. Voyager's own measurements confirmed that the heliosphere blocks more than 70% of that incoming radiation from ever reaching us. For decades, that protective shield was treated in most models as a relatively stable, fixed structure, a known quantity in the broader physics of how our solar system sits inside the galaxy. Voyager's direct measurements suggest instead that the boundary providing that protection is compressed, structured, and shaped by forces that current theory doesn't fully account for. meaning the actual physical mechanism determining how well shielded our entire solar system is from deep space radiation, may be considerably more complicated and less understood than physicists confidently assumed before either spacecraft actually got out there to check. There's a second measurement, arguably even stranger, sitting right alongside the density anomaly, and it involves Voyager's magnetic field data specifically. According to established physics, the magnetic field inside the heliosphere, generated by our own sun, and the magnetic field of the wider galaxy, generated by entirely different processes operating on a vastly larger scale, should point in noticeably different directions. They're produced by unrelated physical mechanisms after all, and there's no obvious reason they should happen to line up. When Voyager 1 and later Voyager 2 actually measured the magnetic field direction on both sides of the heliopause, that expected shift largely failed to appear. The magnetic field just outside the boundary looked strangely, persistently similar in orientation to the field measured just inside it. That similarity remains, even now more than a decade after Voyager 1's original crossing, a genuine, unresolved puzzle. It suggests our current understanding of exactly how the sun's magnetic influence interacts with the broader magnetic structure of the galaxy, beyond it, is missing something important, some interaction or connection between the two fields that existing theory doesn't currently explain. Don Gurnett, a physicist at the University of Iowa who worked directly on the Voyager mission from its earliest days back in the 1970s, has spent years studying exactly this kind of anomalous data, describing the analysis of the interstellar medium as one of the mission's most quietly significant scientific legacies, arriving decades after most people assumed the mission's major discoveries were already behind it. John Richardson, principal investigator for the plasma science experiment aboard Voyager 2, captured the feeling of working with data like this in strikingly direct terms, describing the sensation of genuine exploration, precisely because everything the mission is measuring out there is new, uncatalogued, and unprecedented, with no existing data set to check against, and no way to know in advance whether a given reading will confirm existing theory or completely undermine it. It's worth being precise here about exactly what has and hasn't actually happened to physics as a result of these measurements, because overstating it would be its own kind of dishonesty. Voyager 1 has not discovered a new fundamental force, has not broken any established law of physics, and has not overturned relativity, quantum mechanics, or any of the truly foundational frameworks underlying modern physical science. What it has done is something narrower, but still genuinely significant. It has revealed that a specific applied model describing exactly how the boundary between our solar system and interstellar space behaves, how dense the material is there, and how the magnetic fields on either side of that boundary relate to each other, does not match the real, physically measured universe. That's not a failure of fundamental physics. It's a failure of a specific, applied theoretical model built from indirect remote observation, now being corrected using direct, in-place measurement for the very first time in human history. That distinction matters, and it's actually the more interesting story, not a lesser one. Throughout the history of science, this exact pattern, a well-constructed theoretical model built from indirect evidence, later revised or overturned once direct measurement finally becomes possible, has repeatedly produced some of the most important advances in physics and astronomy. Voyager's interstellar measurements fit squarely into that same tradition. Before Voyager 1 and Voyager 2 actually crossed the heliopause and took direct readings, everything scientists knew about the boundary of our solar system came from models built using remote observation from well inside the heliosphere, extrapolating outward based on assumptions that had never actually been tested against a real physical measurement taken at the boundary itself. Voyager made those models testable for the first time, and testing them revealed real, meaningful gaps between prediction and reality. NASA has been transparent about exactly how significant and exactly how unresolved these findings actually are. Both the density anomaly and the magnetic field alignment puzzle remain active areas of ongoing research, discussed in published papers, conference presentations, and continued analysis of Voyager's data years after the original crossings occurred. Nobody involved in this research is claiming to have a complete, settled explanation for either phenomenon. What they have is real, confirmed, repeatedly verified measurement data, directly contradicting specific predictions from established models, and an honest, ongoing scientific effort to figure out exactly what physical mechanism is actually responsible for the gap between theory and observation. There's also a very real and very literal ticking clock attached to how much more of this specific kind of data humanity is going to be able to gather. Both Voyager spacecraft run on radioisotope thermoelectric generators, nuclear batteries converting the heat of decaying plutonium into electricity, and that power supply shrinks a little more every single year as the radioactive material inside gradually decays. NASA has already been forced to shut down instrument after instrument on both spacecraft, one at a time, specifically to conserve enough remaining power to keep the most scientifically valuable systems, including the instruments responsible for these anomalous density and magnetic field readings, running for as long as physically possible. There is no other spacecraft anywhere near this region of space capable of continuing this measurement if either Voyager finally goes silent, and no funded, built, or launched mission currently exists that could reach interstellar space again for decades, even under the most optimistic possible timeline. Which means every additional month, either spacecraft continues transmitting adds more data to a physical puzzle that, right now, in 2026, still doesn't have a complete, agreed-upon solution. Scientists are not simply waiting for more data to come in and confirm what they already suspect. They're genuinely still working out what physical process could actually be creating this specific combination of unexpectedly dense plasma and an unexpectedly aligned magnetic field, using measurements gathered by two machines that were originally designed in the 1970s to study Jupiter and Saturn, and never intended to still be operating, let alone still generating genuinely unresolved physics questions, nearly half a century later. What makes this story worth telling, honestly, without inflating it into something it isn't, is that the real confirmed version is already remarkable enough. Voyager 1 and Voyager 2 didn't rewrite the fundamental laws governing the universe. They did something almost as significant, in its own quieter way. They proved that a specific, confidently held model of how our solar system's boundary actually behaves was measurably, repeatedly wrong, using direct physical evidence gathered from a place no instrument had ever been able to reach before. That gap between prediction and reality remains open today, actively studied, genuinely unresolved, and entirely dependent on two aging, single-string spacecraft, continuing to transmit for as long as their shrinking power supplies will allow.